Hi everyone. Today we are going to be doing a couple of word problems using our counting principles that we learned in our previous video. So we're going to start off by reviewing what those counting principles were and then seeing how we can apply those to a couple of different situations. In our last video, we found that we could find the probability of an event by taking the number of outcomes in that event and dividing by the total number of outcomes. And we counted rolling two dice. We counted rolling two dice. One problem is when the number of outcomes is very large. So we can use our counting principles to help us out. If you remember, we had that maze with the mice in it, and we have two different events. The number of ways to pick A and then B was equal to the number of ways to pick A times the number of ways to pick B. So we have those four paths, and then for each path we took, there were three more paths we could take once we looked at our second set of paths. We also saw the number of ways to go through A or B. If we started in the middle, was the number of ways to pick A plus the number of ways to pick B. So we can use these counting principles to help us out with answering some word problems about probabilities. Let's take a look at our first word problem. So at a nearby restaurant, there are two different cup sizes and 8 sodas to choose from. And you always randomly choose a cup size and a soda. You like to live dangerously. Problem number 1 is looking at the probability of ending up with a large Coke. So for these situations, it can sometimes help to draw a quick model. So you can think about starting here. You can pick either, let's say, a large or small cup size. And then for each of those, you have 8 different choices for the type of soda. So 1, 2, 3, 4, 5, 6, 7, 8. And down here, 1, 2, 3, 4, 5, 6, 7, 8. So 8 different sodas you can choose from. So looking at this model, the number of choices that we end up with over here are 8 plus 8, which is 16 total different combinations of cup sizes and sodas. So we could pick a large of any soda, so that's 8 choices, or a small of any soda. So looking back, what is the probability of ending up with a large Coke? Well, a large Coke would be going down the large path here, and then choosing the Coke option here. So there's one possible outcome in this event out of 16 total outcomes. One outcome out of 16 total outcomes. So 1/16 is the probability of ending up with a large Coke. Number 2 is looking at the probability of ending up with either a Sprite or a Coke. Here, we could use our original model. What's nice about situations like this is we can actually switch the order that we're making these decisions in and start instead with the flavor of soda that we're choosing. So we could start with 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different sodas. And then for each soda, we have 2 options, large or small. Large, small, large, small. And we end up with 16 total options in the end. Here we're looking at the probability of ending up with either a Sprite or a Coke. So what we can do is look at the soda options. Maybe the first option is Coke. The second option is Sprite. And notice it doesn't matter what size we choose because we're just looking at the different types of sodas. So here, Coke and Sprite are 2 outcomes in our event. The number of outcomes that aren't in our event, or the total number of outcomes over here, are 8. You could also look at, so we're ignoring cup size, you could also look at including cup size. So large or small Coke, large or small Sprite. So we have 4 outcomes in our event here out of a total of 16. 4 out of 16 or 1 out of 8. Sorry, 2 out of 8. And notice these are the same probabilities. So we end up with the same answer, whether we consider cup size or don't consider it. So 2 out of 8, 4 out of 16, which is, of course, 1/4. Finally, we're being asked to find the probability of ending up with either a large size or a Coke. And looking at number 2, the counting principle we used here is either a Sprite or a Coke. So we took the number of Sprite ways and added it to the number of Coke ways. So notice we had 2 Coke ways and 2 Sprite ways. So 2 plus 2 is 4 events, or 4 outcomes in the event. Finally, the probability of ending up with either a large size or a Coke. So for this one, I'm going to return to our first model. We're looking at either a large size or a Coke. We started off by splitting it up into large or small. So all of these outcomes here are in our event. Any large size works out. The probability of ending up with a Coke, well, one of the probabilities is over here in the large size, which we already counted. We also want to consider what happens if we end up with a small Coke. So we have one other way that we could end up with a Coke, and that's if we choose small and then choose Coke. So all in all, we have 8 different large sizes, and we have 1 Coke size in the small. So 8 plus 1 is 9 total outcomes in our event. And again, this is out of 16 total outcomes for all the possible combinations of size and type of soda. So 9 out of 16 is our probability here. So as you can see, drawing a model can help us out. And here we're just using some of our counting principles. All right, and one quick thing to watch out for is we don't have 2 Cokes that we counted here because our option of choosing a Coke and choosing a large can occur at the same time. So up here we end up with a Coke and a large. And if our 2 options could occur at the same time, we can't just add them up. We have to be careful and make sure we don't count this option over here twice. So we don't want to count that twice. So we counted all of the larges and then 1 additional Coke. Looking at another example problem here, Frederick forgot to complete his daily lesson on Duolingo, and the Duolingo bird is hunting him down. There are 25 different languages, and each of them have a basic, intermediate, and advanced category. And we're assuming there's an equal chance he's studying any language, any category. Maybe he's really good at languages, or maybe not. Maybe he's basic. We'll see. First, we're looking at the probability that Frederick will be forced to complete a lesson in the basic category for either French or Spanish. All right, so again, we can draw a model. Let's start off with Frederick. And he's a little scared because he's running away from the Duolingo bird. And we can start with 3 different categories: basic, intermediate, and advanced. And then for each category, there's the 25 different languages. So here we have 25 different languages, here we have 25, here we have 25. So instead of drawing out 25 spaces for each one, I'm just going to write the number for now. We're looking for the probability that Frederick will be forced to complete a lesson in the basic category for French or Spanish. So in this situation, we're looking only at the basic category, and we're looking for French and Spanish. So of these 25, we know that French is one of them, and Spanish is another one of them. So we have 2 outcomes in our event here out of a total of, well, we have 25, 25, 25, out of a total of 75 outcomes. So for number 1, our answer is going to be 2 out of 75. So only in the basic category, only French or Spanish. And again, or we can add these up. There's 1 outcome for French, 1 outcome for Spanish. Number 2 is looking at the probability that Frederick is going to complete an advanced lesson or a German lesson. So here, again, we have to be a little bit careful when we're going through finding this probability. So we're looking at completing an advanced lesson down here. So all of these count in our outcome, or count as outcomes in our event, or a German lesson. So we know there's a German in the basic category, there's a German in the intermediate category, there's a German in the advanced category, but we already counted this German down here. So we don't want to count this twice. So instead of taking all of the possible outcomes in the advanced space, which is 25, and adding all of the possible German outcomes, 3, we're going to be careful. We're only adding these other 2 outcomes, because for our third one, we already are in the advanced category, so we already counted that over here. 25 plus 2 gives us 27, and again, that's out of 75 total outcomes. 27 out of 75 is our answer for number 2. All right, so finally we're looking at 10 students in a class and 10 chairs numbered 1 through 10. So first, how many ways could a student be selected to occupy chair 1? So some of these might seem straightforward, but one thing to watch out with for probability is sometimes the answer isn't always intuitive, or it isn't always obvious right away. Number 1 is pretty easy. So here, how many different ways could a student occupy chair 1? Well, we have our 10 chairs. Chair 1, 2, 3, 4, and so on. And of the 10 students, we know that we're choosing 1 of those students. So there are 10 different students who would go in that first chair. So for number 1, we have 10 different ways that chair could be filled. Number 2 says after someone has been seated in chair 1, how many different ways are there of seating someone in chair 2? You might think, okay, chair 2, 10 ways, same thing as chair 1. But one thing to watch out for is the word after someone, or the phrase after someone has been seated in chair 1. So 1 student has already been seated. So looking at chair 2, we actually only have 9 students left to choose from. So number 2 is going to be 9 ways. Number 3 is asking in how many different ways could chair 1 and chair 2 be filled? We could think about number of ways to fill A, chair 1, and then B, chair 2, which, if we think back to our counting principles, is equal to the number of ways to fill chair A times, or chair 1, times the number of ways to fill chair 2. So 10 times 9, which is 90. So we have, for number 3, 90 ways. And one way to think about this is we could choose our first student here to fill chair 1, and then we have 9 different students, the other 9 students we could choose from once we fill chair 1. With student 1, we could then choose student 2, and we have 9 more. So we have 10 times the students, and then 10 times 9 for filling out the second chair. Number 4 is looking at if the first 2 chairs are already occupied by students, and how many ways could chair 3 be filled. So again, here we've already filled the first 2 chairs. So for chair 3, we only have 8 students left. So 8 ways. Number 5 is asking in how many different ways could the first 3 chairs be filled. Here we can extend our counting principle, number of ways of A, then B, then C is equal to the number of ways for A times the number of ways for B times the number of ways for C. So 10 times 9 times, and then we saw 8. So 90 times 8 is 720. So for number 5, we have 720 ways. So as you can see, the number of ways increases dramatically as we increase the number of chairs. We started with 10, then 90, then 720. Number 6 is asking how many different ways could all 10 chairs be occupied. What's happening here is we can keep going. 4, 5, 6, 7, 8, 9, 10. So we have our 10 chairs. And each time we move on to a chair, we're going to have one less student to fill the chairs. So we have 7 different students for 4. And these circles are kind of like the student's head, for example. These shouldn't be confused as zeros. So 7 students, 6 students, 5, 4, 3, 2, and finally for the last chair, there's only 1 student left over. So what we're doing is we're extending this A, then B, then C for all 10 chairs. So we start off with 10. Second chair is 9 different students. Third chair is 8 different students. 7, 6, 5, 4, 3, 2, 1. And we'll learn about this in our next videos. This is what we call 10 factorial. So we have an exclamation mark. And again, we'll be learning this in our next video. So if we multiply all of these out on a calculator, we end up with the number 3,628,800. 3,628,800. So this is the number of ways we could fill all 10 chairs. So as you can see, that number increased very quickly from 10 to 90, 720, all the way to over 3 million ways to fill the chairs. So sometimes we end up with very large numbers in probability, and this is where these counting principles can help us out. So a few quick just takeaways from our lesson today. We went over our 2 counting principles. The number of ways for A then B is number of ways for A times number of ways for B, and we can extend this principle for more options. We learned that, or we reviewed the counting principle here, number of ways of A or B, we can add them, but that's only if A and B can't both occur. So if they do both occur, we want to count these overlaps once. So looking back at our second example, the German language was already counted when we counted the advanced ones, so we're not counting it again. We're only counting these 2 German languages when adding them up.